This video is supported by the NDLR and the Department of Mathematics in NUI Maynooth. In this video I want to introduce you to the idea of calculating limits to infinity. So let's begin by trying to calculate the limit as x goes to infinity of 1 over x. So what this is saying to us is, if you were to let x approach infinity or increase without any kind of bound whatsoever, what would the value of 1 over x be? So to help us solve this problem, I've got a graph of the function 1 over x. So looking at this graph here, hopefully you'll agree that it would appear that as the values of x get bigger and bigger, the corresponding y values seem to be getting smaller and smaller. So we might guess that if we were to let x approach infinity, the corresponding y value would be 0. But let's see, can we work that out? Okay, so remember what this is saying to us. As x goes to infinity or increases without any kind of bound, what would the value of 1 over x be? So let's think about fractions for a second. When it comes to fractions, if we were to fix the top value, well, as the bottom gets bigger and bigger, the corresponding value of the fraction itself will get smaller and smaller. So in our case, if we were to let x go to infinity, or in other words let x increase without any kind of bound whatsoever, 1 over it is going to go to 0. Okay, let's try another example. This time, let's try and calculate the limit as x goes to infinity of 1 over x squared. So what this is saying to us is, if we were to let x approach infinity or increase without any kind of bound whatsoever, what would the value of 1 over x squared be? So just like in the first example, I've got a graph of the function 1 over x squared to help us out. Okay, so hopefully you can see that as the values of x are increasing, the corresponding y values seem to be getting smaller and smaller and smaller. And we might guess that if we were to let x go to infinity, the corresponding y value would approach 0. But let's see, can we work that out? Okay, so this example is very similar to the first one. The only real difference is that we've got a square here on the x, which we did not have in the first example. So we might ask the question, what effect does this squaring have on the x? So let's think about it. As x goes to infinity, so in other words, as x increases without any kind of bound at all, well, squaring it just means that this bit on the bottom is going to get bigger even quicker than it did in the first example. So all this squaring does here is just forces 1 over it to approach 0 quicker than it did in the first example. So the next step is to try and generalize this idea. If we let p be an element of the natural numbers, then let's try and calculate the limit as x goes to infinity of 1 over x to the p. Okay, so let's think about this. This is saying to us, if we were to let x go to infinity or increase without any kind of bound whatsoever, what would the value of 1 over x to the p be? Okay, so let's think about this. Well, p is an element of the natural number. So in other words, p here is a positive whole number. So we might ask the question, what effect does p have in this problem? So just like we had the second example here where we had the square, what p does is it dictates the rate at which this bit on the bottom is going to increase. Remember, x is going to infinity. So the bigger the value of p, the quicker this bit on the bottom is going to increase. But the important bit to realise is that this bit on the bottom is still going to infinity, just at different rates depending on the value of p. So in total, 1 over this x to the p is still going to go to 0. Again, it's going to go to 0 at different rates, just depending on the value of p. This is an important fact, so I'm going to put it in a box because we want to refer to it later. The next step I want to do is to try and generalise this a little bit further. This time we let n be an element of the real numbers, and we let p be an element of the natural numbers like we had above. And this time I want to try and calculate the limit as x goes to infinity of n over x to the p. Okay, so remember, n is a real number and p is a natural number. So using my rules of limits, because n is just a constant, I can take it out the front. So in other words, I can rewrite it as n times the limit as x goes to infinity of 1 all over x to the p. But hopefully you'll agree that this bit here, this limit, we've already calculated. It's here above in this box. We know that this limit is 0. So in other words, I can rewrite this as n times 0, which of course is just 0. So this is important, so I just want to rewrite it again. So we have let n be an element of R, and we have p be an element of the natural numbers. Then the limit as x goes to infinity of n all over x to the p is equal to 0. So this is an important fact, and I suggest you commit it to memory.